This is Calculus 1.5. Today we're going to determine limits using algebraic properties of limits. And honestly, a lot of this is common sense. As long as you know you can substitute the C value into what they give you for the limit, most of this stuff is pretty self-explanatory, but I need to show you the properties that work because you're going to find occasions where it might make it easier on your math if you separate each limit out separately and separate the different parts of the function out. And so this just shows you what you're allowed to do. And it really is pretty much common sense, but I want to make sure that you see some examples and how this works. So these are properties of limits. And basically for every one of these properties, we're going to say that B and C are real numbers and that N is a positive integer, okay? And I've got three different properties here, and these are very simple properties, and then we'll get into properties of some functions after this. So the first one is the limit as x approaches c of b will equal b. Now remember, b and c are real numbers. So if c is a number and b is a number, and they could be the same or different numbers, it really doesn't matter, then the limit as you approach c is going to be equal to b. So here's an example. We want the limit as x approaches 4 of 10. Well, that is just going to be 10. Now, you might be saying, why does that work that way? Well, if you remember, this right here is a function, okay? So if my function, let's just say this is f of x equals 10, okay? Well, if that is a function of f of x equals 10, wouldn't that be the horizontal line that goes through 10? So if that's the case, when x equals 4, my y value is going to be 10. So this is just kind of a horizontal line in disguise there. That's all they've done. So that's what that means. So if you have a number here and a number here, then the limit is equal to whatever that function number was. For the second one, the limit as x approaches c of x equals c. Now x is a variable here. Anytime we have a variable, remember, as x approaches that number, we can just plug that number in for the variable. So this is direct substitution. And a lot of times in limits, direct substitution will work, and it just makes it really simple. I've kind of showed you some of the background information with limits now. Now we're going to head into where algebra will really help us solve those. So if I plug c in for x, I end up with c as my answer. So here's a simple example. The limit as x approaches 2 of x. I'm going to plug 2 in for x, and my limit there will be 2. So pretty simple. Let's look at the next one. The limit of x to the n as x approaches c. Well, remember, if x approaches a number, that number can then be put in for x. So we're going to replace x, or do direct substitution, with that c in for x. So it will be c to the n. So an example of that, the limit of x squared as x approaches 5. I'm going to direct substitute that 5 in for x. That will give me 5 squared, which is 25. So very simple basic properties there. In this segment, we're going to talk about what happens to limits when functions are combined within the same limit. And we have several examples here with the properties. There are going to be 5 of these total. And with these, we're going to still have b and c are real numbers. N is a positive integer. And f and g are going to be functions with these limits. So the limit as x approaches c of f of x is going to be L. And the limit as x approaches c of g of x is going to be K. And our first property is kind of scalar multiplication. The limit of b times the function f of x as x approaches c. Now, we could direct substitute the c in, but you need to understand that when you do that, this is the property that will happen. That b has been multiplied by the entire function. So we're allowed to take the b out to the front and then multiply the limit times b to get our answer. So if we bring out that b, the number that everything has been multiplied by, and then find the limit of the function like normal, and they told us that the limit of f of x is L, then the limit of this entire function is going to be b times the limit of f of x. So that's b times L. So an example of that would be right here. If we have the limit as x approaches -2 of 4 times x squared minus 16, hopefully you notice there that the 4 has been multiplied by that entire function. So I can bring it out. That's 4 times x squared minus 4. And then I can take the 4 and move it to the front of the limit. So that's 4 times the limit as x approaches -2 of x squared minus 4. And so then -2 plugged in there would be 4 minus 4 is 0, and 4 times 0 is going to give us 0. So we would have gotten the same thing if we had just plugged in -2 here, or if we distribute out the 4. Now, you might say, well, isn't it easier for this one to just do this? Yeah, it is. But the properties, if they work for easy ones, they also work for the more difficult problems. In number 2, the property states that the limit of the function f of x plus or minus the function g of x as x approaches c, that can be separated. Okay? Here we have the limit of a sum or the limit of a difference. Okay? The limit of the sum or a difference is the same as the sum or difference of their limits. So we can separate these two into two separate functions and add those limits together. So I can separate this and say it's the limit of f of x as x approaches c plus or minus the limit of g of x as x approaches c. So I've separated them out. I had the limit of a sum or difference, and I made it the sum or difference of two separate limits. And you would get the same answer either way. And so if you know the limit of f of x as x approaches c is L, and the limit of g of x as x approaches c is k, then all you have to do is add those two limits together. So here's an example. I can take that function, and with this one, you know, you could separate this out, plug the 5 in, and then separate this out and plug the 5 in to get your answer. But honestly, if I had this one, I'm just going to plug 5 in directly. So you see how some of the properties are a little redundant, but in some specific examples, it does help to understand that these things can be separated out. So I'm going to go ahead and do that, showing you how the property works. That is the same thing as the limit as x approaches 5 of x squared plus the limit as x approaches 5 of natural log of x. Then I'm going to do direct substitution. So if I plug 5 in for x, I get 25. If I plug 5 in for x here, I get the natural log of 5. So the answer is 25 plus natural log of 5, which would be the same if you did direct substitution right away, right off the bat. So a lot of the properties can be redundant. They can be very simple. A lot of times you don't need to use them, but it's good to know you have them available if you need them. So we have 3 more to do. Let's get to those. Okay, property number 3. We're looking at the limit of f of x times g of x as x approaches c. That can be separated just like we did for addition and subtraction. So that's the same as the limit of f of x as x approaches c times the limit of g of x as x approaches c. So that would be the f of x limit L times the g of x limit K. So if I have something like this, basically all that is saying is that I can separate that into 2 separate problems. The limit as x approaches 1 of x plus 3 times the limit as x approaches 1 of x minus 2. And then if I do direct substitution, I would have 4 times -1, which is -4. Hopefully you notice that if I just direct substitute 1 in right away, we're going to get the same thing. So honestly, it's not any more, well actually this really causes you extra work. If I were to give you an equation or a limit problem like this and ask you to solve it, I want you to do it as efficiently as possible. So sometimes the properties do add extra work, but you need to know you can use them if you need them. All right, for this one, the limit as x approaches c of f of x over g of x, or divided by g of x. That's the same thing as taking the limit of the top over the limit of the bottom. So the limit of the top would be L, the limit of the bottom is K. An example of that, we could separate that out if we wanted to. That's the same thing as the limit as x approaches 1 of x squared plus x plus 2 over the limit as x approaches 1 of x plus 1. And if I do those separately, if I plug 1 in here, I've got 1 plus 2 is 4. If I plug 1 in here, I get 2. So my answer will be 2. Pretty simple. So again, direct substitution is just as easy, probably easier than writing it out. This causes you a little bit more work in this case. And then the last property, the limit of f of x to the nth power as x approaches c. That can be separated out to where we take, since this is the exponent and it's applied to the function, we can take the limit of the function first and then apply the exponent. Okay, so we can make that whole thing to the power of n. So if we know the limit of f of x is L, we can just take L to the n power there. So here's an example of this. I can rewrite that as the limit as x approaches 2 of 2x all to the third power. And so then if I plug 2 in, I get 4. 4 cubed is 64. Again, it's just as easy to do it right there. It means the same thing. Okay? So those are your properties for limits. I have 9 problems here. Go ahead and copy the problem, pause the video, see if you can do these on your own, and then I'll come back and give you the answer in a few minutes. Okay, doing these together. If I do direct substitution for all of these, if I plug -2 in for x here, I have -2 to the -3rd. Well, we know from our work with negative exponents that we have to move that -2 to the bottom to a positive exponent of 3, and so that will be a -1/8. For this one, we know that that's a whole number as we plug 6 in, so that's going to be a horizontal line. So the answer there, or the limit there, is 5. Here, if I direct substitute 10 in, I just get 10. With this one, doing direct substitution, 2 squared is 4, times 4 is 16, plus 3 is 19. If I direct substitute -1, -1 squared is 1, plus 6 is 7. -1 minus 2 is -3, so -7/3 for that one. If I directly substitute 0 in, 0 squared is 0, plus 4 is 4. Oh, this one I already gave you the answer for, so that one hopefully you noticed was 2. If I plug 0 in here, 0 squared is 0, plus 4 is 4. Square root of 4 is 2. Remember, we only need to put plus or minus if we have an equation that we have put in the square root. Otherwise, we're just looking for the principal square root, which would be the positive answer there. So no need to put plus or minus. Some students have trouble with that at first. So no need to put plus or minus unless you have put in the equation a square root on your own to solve it. And then here we've got a 3 that we're going to substitute in directly. So that's 3 squared is 9, times 2 is 18, minus 10 is 8, and then the cube root of 8 is 2. We will do trigonometry a lot in calculus, and a lot of times your algebraic equations are easier than the trig functions. Trig functions are what makes calculus a little more difficult. And one thing about the trig functions is that direct substitution still works, but what holds some students up is they can't remember how to do trig. So by this point we have reviewed that in my class. If you need reviews, there are all kinds of reviews you could do online. If you need to do that, I would suggest maybe going to Khan Academy and looking up the unit circle and how to find answers from the unit circle, because that's predominantly what we will use in calculus when we're solving questions about trig functions. So use the unit circle, okay? So if I plug 0 in for x, we have tangent of 0. So real quick, if I just do a real simple unit circle at 0, my ordered pair is 1, 0. So the trig function would be sine over cosine. So sine is the y value, cosine is the x value. So sine over cosine would be 0 over 1. So tangent at 0 is 0. Here we have the limit as x approaches pi of x cosine x. So we are at pi, okay? At pi, that ordered pair is -1, 0. Cosine of the ordered pair is the x coordinate. So cosine at pi is -1, and -1 times pi is -pi for my answer there. Here I have the limit of sine squared x as x approaches 0. Well, that's the same thing as sine of 0 squared if we plug the 0 in. So sine at 0 is 0, and 0 squared is 0. So that's just a quick review of some trig functions. I always tend to draw just a little unit circle to help me with it. Remember, they're only going to do your 30, 60s, and 45, 45 triangles plus your quadrantal angles. Your 0, 90, 180, 270, 360 angles. Other than that, the calculator has to be used for trigonometry. Next, I want to talk about one-sided limits and make sure you understand why direct substitution sometimes won't work for these. If this is my function f of x equals 1 over 2 times x plus 1, a lot of times with one-sided limits, what they're going to do is they're going to ask you to find the limit of some function from the left, from the right, and then the total limit. Now remember, in order for this one to have a limit, both of these have to be the same because it has to approach the same number from the left as it does from the right. So when you have one-sided limits, it's not always going to be as easy as just plugging directly in and doing direct substitution. Sometimes it is, but most of the time you're going to have to do a graph, okay? And here's why. If I were to direct substitute the -1 in, if you look at what happens here, that gives me division of 0 on the bottom. So I know that at -1, there's going to either be a hole or an asymptote in my graph. So I'm going to have to do a little further investigation to see what's happening here. So I'm going to just do a quick little graph. And if you look at this function, there is no way to cancel out the 0 on the bottom because there's nothing on top to factor out and cancel. So that pretty much tells me it has to be a vertical asymptote. So at -1 in this function, we're going to have a vertical asymptote. And then what I would do at this point, I would use a calculator to graph my function. I would just put it directly in and graph it and see what it's going to look like. We'll review horizontal asymptotes a little bit better later, but hopefully you see that since the exponent on top is less than the exponent on the bottom, or the degree on top is less than the degree on the bottom, then our horizontal asymptote is y equals 0. And so when I put that into my calculator to see what the graph is doing, this is what the basic graph looks like. It's going down in that direction and then up this way. So it's going up towards -1 as you approach from the right, down towards -1 as you approach from the left. So if we're doing one-sided limits, the limit as x approaches -1 from the left, well, as it approaches -1, it's approaching -infinity. The limit as x approaches -1 from the right, well, it's approaching infinity. And then the limit as x approaches -1, in order for that to have a limit, these two things have to be the same. Are they the same? They are opposites. Since they're not the same, the limit as it just approaches -1 does not exist. So the one-sided limits exist, but the full limit does not because they don't approach the same thing from both directions. So here I have two more examples that are going to require you to do some graphing. You're going to have asymptotes at the number where I'm asking you to plug in. So I want you to go ahead and copy these down, see if you can get the graph, see if you can understand the one-sided limits, and then I'll come back and explain them after you've had a chance to do them. So go ahead and pause the video. Okay, so looking at the first one, if you were to direct substitute the -1 in, -1 squared is 1 and 1 minus 1 is 0. So with that, we know we have division by 0, so we know we're either going to have an asymptote or a hole there. And then when we do some further investigation to see if we can cancel anything out, notice on the top, that's not factorable. But on the bottom, it is. That's x plus 1 times x minus 1. So when I see that, and I see that nothing cancels out, that tells me I'm going to have two asymptotes. One at -1 and one at 1. Because if I set the denominator equal to 0, remember, I have to set each individual factor equal to 0. And when I do that, I get x equals -1 and x equals 1. So I actually, in fact, have two separate asymptotes for this equation. And this is something that should be familiar to you already. We did this, or you should have done this, in Algebra 2. And then hopefully again in pre-calculus. So you should be well versed in this stuff. So we have two asymptotes, one right there at -1 and another one there at 1. Move that over. And so then looking at the degree of the top and the bottom, notice that the degree of the top and the bottom are the same. So for horizontal asymptotes, it's going to be the ratio of the leading coefficients, remember. So the leading coefficients were both 1. So y equals 1 over 1 would be my horizontal asymptote. So I have a horizontal asymptote here at +1, so right there. And so those are my asymptotes. I need to see what my graph is doing. Now normally, when I have something like this, I have a curve either here or here, and then either here or here, and then this will look kind of like a parabola, either going up or down, depending on what you have. So at this point, once I know what my asymptotes are, I do that by hand, because sometimes the calculator, you're not going to be able to tell where those asymptotes are. The calculator will graph the line, but it's not going to graph the asymptotes so you can see exactly where they are. So if those asymptotes end up being fractions or decimals, which sometimes they are, unless you know exactly where they are, you might get these wrong. So you should do your asymptotes by hand if at all possible, and then use the calculator to help you determine what's happening in each of the different sections. And when I did this on my calculator, this one approaches the asymptotes there, and it's got a kind of a parabola looking portion right there. It's not a parabola, understand, that's not a quadratic. This is a rational function, so it's not, that is not a quadratic. And then in the third section, it does this. So if I look at this approaching -1 from the left. Now, understand, this is what our graph looks like, but we're never going to have to approach 1. These are all approaching -1. So we're only interested in what's happening on this part of the graph. So as x approaches -1 from the left, going this way, it's approaching infinity. As x approaches -1 from the right, well, it's approaching -infinity. And as x approaches -1, since these two things are different, the one-sided limits exist, but the whole limit does not, because they're approaching two different things from each side. The next example is a trig function, f of x equals tangent x, and it looks like we're approaching pi/2 from the left and the right, and then they want the final answer pi/2. Hopefully you remember when you did trig functions that at pi/2, if I do a simple unit circle here, this is pi/2, so that ordered pair is 0, 1. So tangent at pi/2 would be 1 over 0, which is undefined, so direct substitution is not going to work for us here. So hopefully you remember when you learned how to graph your trig functions on a coordinate system, your asymptotes were at your pi/2, so this is at 0. Here's pi/2, there's pi, 3 pi/2, and we could go all the way to 2 pi if we want to. We could do the left side, but all we're interested in is these two sections of my graph, okay? And hopefully you remember that your trig function started here. It goes up toward the asymptotes, and remember you have asymptotes at all of your pi/2 functions, and then it goes down in that direction. 0 at pi goes up in that direction and down at that direction. If you don't remember that, search online, graphing trig functions on a coordinate system, and hopefully you can find something that will explain where those things came from. If you have me in class, though, we have reviewed this already, so you should be good to go there. So if we've got pi/2, and that's what we're approaching, if we're approaching pi/2 from the left, Well, it looks like that's approaching infinity. If we're approaching pi over 2 from the right, looks like that's approaching negative infinity. And so my limit as x approaches pi over 2, those two things are different from each side. So that does not exist. So understand, your one-sided limits could exist and your whole limit maybe doesn't exist because the one-sided limits are different. So that's one thing that you really need to take from this. It's very important, especially when you have an asymptote at the place where you're trying to approach, that you understand what's happening with both sides. You can use a calculator to help you with this. You could use Desmos.com to help you with that. You could graph by hand if you're comfortable with that. All of those methods work. Whatever you're the most comfortable with is what you should use.